Hello everyone, my name is Jiadong Shen, and I'm a graduate student from Zhejiang University, China. Today I will show the paper PESC, a Per-System-Call Canary designed for Linux kernel. Stack buffer overflow is a common software vulnerability. I believe all of you have already known stack buffer overflow. To prevent stack buffer overflow being exploited by attackers, StackGuard is proposed. StackGuard is the most widely deployed mitigation measure. Let's look at this piece of code. In function prologue, the return address of the function is pushed into the stack. And to enable StackGuard, the compiler inserts several instructions. The instructions in line 4, 5, 6 read a value named reference canary, and the instruction in line 7 pushes this value into the stack. In function epilogue, the instruction in line 9, 10, 11 compare the reference canary value with the canary value in the stack. If they are not equal, which means a stack buffer overflow may happen, then the program will jump to line 16, call the function stackCheckFail to avoid dangerous behaviors. However, StackGuard works only if the attacker does not know the specific value of the canary. Once the canary value is leaked by software or hardware bugs, the attacker can craft an overflow payload with that canary value. Then the attacker can exploit a stack buffer overflow. Since the canary is overwritten with the same value, the program cannot detect the buffer overflow by comparing the reference canary value and the canary value in the stack. Besides Canary Leakage, the attacker can also get the value of canary with brute force attack. In paper Hacking Blind, the author proposed a byte-by-byte attack. Here we have an 8-byte canary. The attacker can cautiously control the length of the overflow data, and only overwrite the first byte of canary without overwriting the other 7 bytes. In each round, the attacker can overwrite the first byte with different values. If the process crashes, then the attacker can know the value he writes is not the value of the first byte. And if the process does not crash, then the attacker can know the value he writes is the value of the first byte. Here it only needs at most 256 tries to guess a byte. The attacker can use the same method to guess the canary byte by byte. For canary value of 8 bytes, it only needs at most 256 multiply 8 tries instead of 2 to the 64th power tries for brute force attack. In Linux kernel, there are 2 variants of StackGuard. ARM64 Linux kernel 204.19 uses global canary. It uses one canary for all threads. In other words, all threads share the same canary value. As a result, one thread leaking canary will affect other threads. Global canary is generated when kernel is booting. Better than ARM64, x86-64 uses per-task canary. Each thread has its own canary value. Therefore, one thread leaking canary will not affect other threads. Per-task canary is generated when thread is forking. In global canary, the canary for all threads will not change until kernel reboots. And in per-task canary, the canary for each thread will not change after this thread is forked. This makes them vulnerable to memory leak and also gives the chance to brute force attacks. Therefore, our motivation is: can we increase randomness to defeat both memory leak and brute force attack to canary for Linux kernel? To address this problem, our basic idea is to update the canary for each system call. This can defeat both memory leak and brute force attacks. Basically, when an attacker exploits memory leak to bypass Canary, he needs to do the following things. He should first invoke a system call to leak the kernel stack canary. Then he can craft a payload with that leaked canary. Finally, he can exploit the vulnerable system call with the crafted payload. If we update the canary for each system call, the leaked canary in the first system call is invalidated in the second system call. Therefore, we can defeat memory leak. For brute force attack, the attacker needs repeatedly invoke system calls to accumulate the knowledge of the canary. By updating canary for each system call, the attacker cannot accumulate knowledge of canary across system calls. As a result, we can defeat brute force attacks. Based on our idea, we proposed PESC, a Per-System-Call Canary designed for Linux kernel. Let's take the write system call as an example to illustrate the architecture of PESC. When a user invokes a write system call, the process will switch to the kernel space. At the kernel entry, a canary updating logic is inserted. After that, according to the system call number, the system call dispatcher will find the correct system call in the system call table and jump to fulfill the user request. As a result, PESC can achieve a Per-System-Call capability. To update the canary for each system call, PESC leverages a key observation of the system call stack. The system call stack is empty before serving a system call. And when it is serving a system call, the stack will be filled with stack frames. And after finishing the system call, the stack will become empty again. Therefore, we can update the reference canary at kernel entry. In this way, we do not need to check and update the canary in stack, since the stack is empty at that time. To balance the security and the performance of PESC, we designed two variants of PESC. The first one is called PESC-PMC. It uses the performance monitor counter register to generate a new canary. The performance monitor counter register counts every CPU clock cycle. In this way, we only need 1 or 2 instructions to fetch the value of the performance monitor counter register and take it as a new canary. It minimizes the performance overhead, but also reduces the randomness of new canary. The second variant, named PESC-RNG, uses kernel procedural random number generator functions to generate a new canary. It promises enough randomness for newly generated canary, and its drawback is that it introduces higher performance overhead. We implement both PESC-PMC and PESC-RNG on both ARM64 and x86-64 platforms. PESC-PMC's low randomness may cause the security problem. Therefore, we need to evaluate the security of PESC-PMC. Actually, the best an attacker can do to bypass PESC-PMC is to leak the canary in one system call and use this leaked canary to guess the canary in the next system call. Therefore, our evaluation method is to call the same system call twice consecutively, and count the difference that the canary in the second system call minus the canary in the first system call. Then we can calculate the success rate of guessing the canary in the second system call, with the canary in the first system call being leaked. We test 3 system calls with different lengths: get PID, read, and fork. We use histograms to count the probability distribution of this difference. As is shown in the figure, the x-axis is the value of difference and the y-axis is the probability. As we can find on both ARM64 and x86-64, for all of these 3 system calls, the maximum probability is always smaller than 0.01, This means the success rate of getting the next canary produced by PESC-PMC is always less than 1%. Besides security evaluation, we also evaluate the performance overhead of PESC. We conduct 3 tests. Since we mainly added code into the kernel entry, we want to know the overhead to system calls. The first test focuses on individual system calls. We test 3 individual system calls, get PID, read, and fork. The result shows the overhead varies from less than 1% to 36.1%. To test the overall system call performance overhead, we also use the Unix bench. The result shows that the overhead of PESC-PMC is less than 1% on both ARM64 and x86-64. For PESC-RNG, the overhead is higher but still less than 9%. For the third test, we test the overall performance overhead to the whole system. We use 3 popular synthetic benchmarks on ARM64 and use the SPEC CPU2006 benchmark on x86-64. The result shows the performance overhead is always less than 1%. This is to say, both PESC-PMC and PESC-RNG only introduce negligible overhead to the whole system. This is because, in a real-world program, system calls are not invoked very frequently. Then it comes to the limitations of PESC. PESC only updates the reference canary in kernel entry. This means PESC only provides stronger protection for system call stacks. For kernel thread stacks and interrupt stacks, PESC only provides the same protection as per-task canary does. However, it is reasonable, since the system call stack is the only stack that is accessible by user. Besides, PESC cannot defend against attacks in one single system call. By constructing gadgets, attackers can leak the canary and then inject crafted payload in one single system call. This attack is proposed in Wu's paper. This attack actually breaks the assumption of PESC. PESC only considers that the attacker needs to craft payload in user space before he invokes the vulnerable system call. Finally, it is a takeaway. PESC generates a new canary for each system call to defeat both memory leak and brute force attacks. PESC leverages the key observation that the kernel system call stack is empty before serving and after finishing one system call. Besides, to balance performance and security, PESC has 2 variants. PESC-PMC takes the performance monitor counter register as the random source, and it provides lower randomness but has higher performance. PESC-RNG takes kernel procedural random number generator as the random source, and it has lower performance but provides higher randomness. That's all my presentation. Thanks.